Every day across America's heartland, a hidden giant is at work, mixing, blending, and balancing billions of pounds of grain, corn, soy, and minerals. All for one purpose: to feed the nation's cattle, the backbone of America's food supply. This is the story of the supergiant feed mixer plants, where technology, engineering, and agriculture meet on a breathtaking scale. From towering silos to roaring conveyors, from micronutrient dosing to precision blending, we'll see how science turns raw crops into perfect feed, enough to nourish millions of animals every single day. Before a steak reaches the dinner table or a glass of milk fills your fridge, it begins here, in the massive feed mills that power the cattle industry. These plants are engineering marvels. Each one can process over 1 million tons of feed per year, running 24 hours a day, 7 days a week. But why do we need such scale? Because America's cattle industry is enormous, more than 90 million head of cattle, each requiring a carefully balanced diet for health, growth, and production. From family farms in Texas to feedlots in Kansas, the demand never stops. So the feed mills must keep running, precisely, efficiently, and safely. The journey starts in America's fields. Vast oceans of corn, soybeans, wheat, and barley. Farmers deliver their harvest to the feed plant, where trucks line up like a moving river of grain. Each truck can carry up to 40 tons of raw ingredients. When the grain arrives, it's tested immediately. Technicians measure moisture, protein, and purity. Every batch must meet strict nutritional standards. Once approved, the grain flows into towering storage silos, some over 150 feet tall, each holding thousands of tons of material. From above, the feed plant looks like a futuristic city. Pipes, elevators, and conveyors linking dozens of towers into one synchronized machine. Now comes the transformation. Massive hammer mills, some the size of shipping containers, grind corn and soybeans into fine meal. The goal: uniform particle size for better digestion and nutrient absorption. Each mill can crush up to 50 tons per hour, generating thunderous sound and clouds of grain dust. But inside the control room, operators monitor everything through digital screens, adjusting temperature, airflow, and grinding speed in real time. Next, the ground meal moves to the mixing chambers, enormous horizontal blenders that can hold 20,000 pounds of feed at once. Here, computer systems take over. Dozens of silos release ingredients in exact proportions: corn, soybean meal, vitamins, minerals, fats, and sometimes probiotics. Each recipe is calculated down to the gram, ensuring the cattle get the right nutrients for their age, breed, and purpose, whether it's dairy production or beef finishing. Feed mixing isn't guesswork, it's agricultural science. Inside every plant is a nutrition lab, where scientists test samples for energy, protein, fiber, and moisture. They run spectrometer scans, compare readings, and adjust formulas daily based on cattle health data. In the past, feed was mixed by hand and intuition. Today, algorithms and data analytics decide the balance. For example, a typical beef formula might include 60% corn, 20% soybean meal, 10% roughage, and 10% supplement mix. All optimized for weight gain and feed efficiency. The result? Healthier cattle, less waste, and lower costs for farmers. Walk inside a super feed plant and you'll see some of the largest moving machines in agriculture. Gigantic conveyors stretch hundreds of feet, carrying tons of feed per minute. Massive mixers rotate with slow, deliberate power, like industrial hearts beating in rhythm. Dust collectors, air filters, and cooling fans keep the environment safe and controlled. At the top of the system, computer screens flash with color-coded indicators, every motor, belt, and auger under constant surveillance. If one machine stops, the whole process can pause. That's why redundancy systems, backup motors, emergency silos, and remote controls are always in place. Not all feed stays as powder. In fact, most of it becomes pellets, small dense cylinders that are easier to transport and store. The pelleting line is one of the most fascinating parts of the process. The blended meal is steamed at 180-degree Fahrenheit, softening starches. Then, it's pushed through steel dies that compress it into uniform pellets. These pellets are cooled, screened, and tested for hardness. Too soft, they crumble. Too hard, cattle won't eat them. It's precision down to the millimeter. Each pellet contains everything the animal needs: energy, protein, fiber, vitamins, in one perfect bite. Once cooled, the feed is ready to move. Bulk loaders fill massive semi-trailers bound for ranches and feedlots across the Midwest. Each trailer carries enough feed for hundreds of cattle. GPS tracking ensures every shipment arrives on time. For smaller farms, automated bagging lines fill and seal 50-pound sacks, stacking them onto pallets by robotic arms. It's a dance of logistics and precision, every hour, every day. From the golden fields of the Midwest to the shining steel of America's superfeed plants, every step of this journey tells one story. The story of how human ingenuity feeds the future. If you enjoyed this deep dive into the hidden world of feed production, hit that like button, subscribe, and ring the bell, because more incredible stories of science, industry, and life are coming your way. Paper is one of humanity's greatest inventions. It carries our thoughts, preserves history, enables education, and even wraps our food. From the ancient scrolls of China to the printing of millions of newspapers every single day, paper has shaped civilizations. But behind every sheet of paper lies a fascinating journey. A journey that begins in the forest, travels through mega factories with machines hundreds of meters long, passes through the roaring engines of printing presses, and often returns again to the cycle of recycling plants to start its life anew. So let's unfold the story, sheet by sheet, of one of the most important materials in human history: paper. Before we dive into the fascinating journey of paper, I'd like to invite you to join our community here on YouTube. If you enjoy learning about how everyday things are made and discovering the hidden stories behind them, make sure to hit the subscribe button and turn on the notification bell. That way, you'll never miss our future videos. Our story begins deep inside managed forests. Contrary to what many think, most paper does not come from old-growth forests, but from sustainable tree farms. These are carefully planted and harvested areas designed to balance industry needs with environmental protection. Workers select trees, mostly softwoods like pine and spruce, or hardwoods like birch and eucalyptus, because of their strong, fibrous structure. Once cut, the logs are stripped of bark, chipped into small pieces, and transported to massive pulp mills. Here begins the transformation. Wood is made of three key components: cellulose fibers, the building blocks of paper; lignin, which binds the fibers together; and hemicellulose. To make paper, we need to extract the cellulose. The chips are cooked under high pressure with chemicals in giant digesters. This process, called the Kraft process, dissolves the lignin and separates the cellulose fibers. What's left behind is a brown, mushy mixture called pulp. But raw pulp isn't yet ready to become paper. It needs cleaning, bleaching, and refining. Impurities like knots, sand, or leftover lignin are removed. Then bleaching agents are used to brighten the pulp, giving us the clean white fibers needed for high-quality printing and writing papers. The pulp is then mixed with water, lots of it. In fact, the pulp slurry at this stage is 99% water and only 1% fiber. Why so watery? Because it allows the fibers to flow evenly onto screens in the next stage, forming consistent sheets. This is the foundation. From towering trees, through chipping, pulping, and bleaching, we now have a raw material ready to be shaped into paper. Now comes the mesmerizing part, turning pulp into continuous rolls of paper. The diluted pulp mixture flows onto a moving wire mesh conveyor called the fourdrinier machine. As water drains away, the fibers begin interlocking, forming a wet mat. Giant suction boxes pull even more water out, and slowly, a sheet of paper starts to take shape. Next, the damp sheet passes through enormous heated rollers. These squeeze out the remaining water while drying the paper under controlled heat and pressure. It's a delicate balance. Too much pressure and the sheet becomes brittle. Too little and it won't hold its form. After drying, the paper undergoes calendaring, a process where smooth steel rollers compress it to achieve the desired thickness and surface texture. This is how we get glossy magazine paper, crisp office paper, or rough cardboard, all from the same pulp, just processed differently. Finally, the finished sheets are wound into gigantic rolls, sometimes weighing up to 30 tons and stretching for miles if unrolled. These rolls are then shipped worldwide to publishers, packaging companies, and printers. At this point, paper is a blank canvas, ready to carry the next big idea. The invention of the printing press in the 15th century turned paper from a luxury into a necessity. Today, modern printing presses run at lightning speed, producing newspapers, magazines, books, and packaging on a massive scale. In offset printing, for example, inked images are transferred from a metal plate to a rubber blanket, then pressed onto paper. The paper zooms through rollers at hundreds of feet per second, each sheet absorbing precise layers of ink. Think about it. That morning newspaper you hold was just a blank roll of paper the day before. Now it's filled with photographs, headlines, and stories, brought to life by printing technology. From political revolutions to love letters, from textbooks to advertising posters, printing on paper has been humanity's way of spreading knowledge, culture, and emotion for centuries. Unlike many materials, paper can be recycled up to 5 to 7 times before the fibers become too short to bind. Recycling plants collect used newspapers, cardboard boxes, office waste, and packaging. The paper is sorted, shredded, and mixed with water to form a slurry again. Ink is removed through a process called de-inking, where air bubbles lift ink particles to the surface. The cleaned pulp is then mixed with fresh fibers for strength. This recycled pulp goes back to paper machines, forming new sheets. Some become newspapers again, others packaging boxes or even tissues. Recycling not only saves trees, but also reduces landfill waste and conserves energy. Each ton of recycled paper saves about 17 trees, 7,000 gallons of water, and enough energy to power a home for 6 months. If you enjoyed this video and want to see more fascinating journeys of everyday materials, don't forget to like, subscribe, and hit the bell icon. It really helps us grow and bring you more educational content from inside the world's most essential industries. Thank you for watching, and remember, the story of paper is also the story of us. Butter, a golden spread that has been a staple in kitchens for centuries. From flaky croissants to sizzling pans, its rich flavor and smooth texture have made it one of the world's most beloved dairy products. But have you ever wondered how factories manage to produce tons of butter every single day while keeping it fresh, safe, and perfectly creamy? Today, we'll go inside a modern butter factory to uncover the fascinating journey, from raw milk to the neatly packaged blocks you see in stores. Before we dive deeper into the fascinating journey of how tons of butter are made, don't forget to hit the subscribe button and turn on the notification bell. That way you'll never miss any of our behind-the-scenes looks at how your favorite foods are created. Now, let's begin. Butter has been a part of human diets for over 4,000 years. The earliest records trace back to ancient Mesopotamia and India, where people discovered that shaking or churning cream separated fat from liquid, producing a rich and spreadable food. In medieval Europe, butter was so valuable it was often used as a form of tribute or trade, and monasteries became known for perfecting its production. By the 19th century, with the rise of industrialization, butter production shifted from small farms to mechanized creameries, making it more widely available. Today, modern factories produce thousands of tons of butter daily, combining traditional techniques with advanced technology, ensuring both safety and flavor for consumers around the world. The process begins not in the factory, but on dairy farms. Every day, hundreds of cows are milked, and their fresh milk is immediately cooled to about 4 degrees Celsius to prevent bacterial growth. Special insulated tanker trucks transport the milk to the factory. Upon arrival, the milk is tested for purity, fat content, and freshness. Any batch that doesn't meet strict quality standards is rejected. The butter-making process requires high-fat cream, so the milk first undergoes separation. At the heart of butter production is the separation of cream from milk. This is done using a machine called a centrifugal cream separator. Inside, the milk is spun at high speed, thousands of revolutions per minute. The heavier skim milk is pushed outward, while the lighter cream collects in the center. The cream extracted here typically contains 35 to 40% milk fat, the ideal starting point for butter. The skim milk isn't wasted. It's sent off to be used in products like cheese, yogurt, or powdered milk. To make the cream safe and extend its shelf life, it is pasteurized. This involves heating the cream to about 85 degrees Celsius for 15 seconds before quickly cooling it down. Pasteurization eliminates harmful bacteria while preserving the cream's natural flavor. It also prepares the fat globules for the transformation into butter. In many butter factories, especially those producing cultured butter, the cream is left to age in large stainless steel tanks. Beneficial lactic acid bacteria are sometimes added to give the butter a slightly tangy flavor and improve texture. The cream rests for 12 to 24 hours, thickening slightly and developing its signature aroma. Now comes the step most people associate with butter: churning. In the factory, massive continuous churn machines handle thousands of liters of cream at a time. The cream is agitated vigorously, breaking the protective membrane around the fat globules. As the fat globules collide and stick together, they form butter grains, while the liquid left behind becomes buttermilk. The sight is dramatic. Within minutes, the cream separates into golden clumps of butter floating in a milky liquid. The fresh butter grains are now drained of buttermilk. This liquid is collected and processed separately, often sold as a refreshing drink or used in baking. The butter grains, however, are not yet ready. They still contain too much liquid, and the texture needs refining. The butter grains are transferred into large butter workers, machines with rotating paddles. Here, the butter is kneaded to press out remaining buttermilk and achieve a smooth, uniform consistency. Salt may be added at this stage, depending on the type of butter being produced. Salted butter lasts longer and has a distinctive flavor, while unsalted butter is prized by